Hello, I'm Murad Kablan. I will be presenting Stateless Network Functions, breaking the tight coupling of state and processing. The backdrop for this work is that networks need network functions, such as firewalls and load balancer, to protect and manage the network traffic. The study have shown that there can be hundreds to thousands of these in networks. However, in today's world, networks need agile network functions to match the agility of the rest of the infrastructure. With servers and storage, we are now able to launch applications in a matter of seconds, adjust the amount of storage that we have on demand instantaneously as application needed. And we are able to scale the application in and out over time with the minimum effort. But with network functions, we don't have the same type of agility. And why do we need network agility? Well, nowadays we have exponentially increasing data traffic in networks, number of devices connected to networks, and scale and complexity of security threats. Network functions today have to deal with all of that, and the current solution falls short, as we will see next. To match the definition of agility, which is ease of use and quick deployment, network functions need to have three features: seamless scalability, the ability to scale up and down without disrupting the network traffic; failure resiliency, the ability to detect and recover from failure, again without disrupting network traffic; and finally, instant deployment, the ability to instantly launch network functions and configure their scalability and failure resiliency. All of this making managing infrastructure easy. And with that, we can focus on what we really care about, which are the functionality of the applications. And most importantly, doing all of the above without sacrificing performance of network functions in terms of throughput and latency. So you may ask, virtual networks functions to the rescue, right? Recently, each of network vendors have started offering out virtual machines of their appliances. There is even plug-in to OpenStack and other orchestrators to manage those virtual machines. But are these really the solution to provide network agility? We argue no, and it's because the same core architecture and same fundamental limit. Yes, you no longer have to physically plug in a box, but in terms of agility beyond that is still limited. So what's the exact problem with the current architecture? The challenge has to do with how state is handled, and more to the point, that is not handled. State is integral to the functionality of network functions. For example, firewalls track the state of connections, load balancer, remember mapping to backend servers, intrusion prevention system track the automata state, and NAT store the mapping between internal and external addresses. So why does the state matter? Let's take a look at handling failure. Here, a packet goes through a device, such as a firewall, and some state is created. If that device fails, we can spin up a new instance, but when the traffic goes to that device, the lookup fails because there is no state. The scaling out is also causing problems. We should be able to add more processing capacity as the traffic grows and shrink it when traffic drops. For scaling out, we can't simply direct traffic to a new instance, because similar to the failure case, the state won't be there. So we have to deal with period of imbalance. And scaling in is also a challenge, as we can't merge devices which are both underloaded, but instead need to wait until all flows have ended. A situation which is difficult with longer-lived flows, such as web apps using WebSockets that are designed to eliminate having to pay setup penalty for each HTTP request. And finally, asymmetrical multipath becomes a challenge, because we need all the traffic from the same flow in both directions to go to the same instance where a state is stored. This forces the need to coordinate forwarding to ensure flow affinity. Now, we are not the first to raise the issue of state and network functions. Both industry and academia had tried to address the challenge with state. Industry have been dealing with state largely in two ways, and each has limitation. One, traditional approach for dealing with reliability is having high availability pairs. Because the instances have to sync their state, this has a huge overhead, and such systems cannot scale to more than 2 instances. This really caused the industry to scale up, meaning getting a bigger box rather than scaling out. Two, to deal with the scale, there are approaches where people have designed the applications to not use state at all. The main reason is to obtain elasticity and resilience, but also that's mean limiting such systems from adding new applications or features. In academia, multiple research projects have also been working on the problem of state. For example, a main approach proposed to handle scaling is state migration. With this, hooks are added to the network function code to allow state to be exported from one instance to another. This only handles planned events, generally has moderate overhead to perform the migration, and limits flexibility as it relies on flow affinity. On the failure side, a proposal is to perform periodic checkpointing, which allows for quick recovery from failure by restoring to a checkpoint. With domain-specific knowledge, the amount of state can be reduced, but it has a high packet latency associated with this approach. To improve on the latency, rather than checkpointing state, other solutions log events, such as upon failure, we can rebuild the state by replying those events. This improves on the packet latency, but at the expense of having long recovery time. And in addition to have the trade-off between long packet latency and long recovery time, in both cases, neither added scalability or asymmetric routing case. So in this work, we ask what the root of the problem really is. And our conclusion is that is the appliance mentality. In each of the previous work, network functions were viewed as individual appliances, with tight coupling between state and processing. So here we ask, what if we redesign network functions as a distributed system from the ground up, where we can decouple the state from the processing? Here we call them stateless network functions. The network applications, such as firewalling, are still stateful, but the functions themselves are stateless. This is a design that had made applications scalable and resilient in other domains, such as web services. As we showed in the problem with coupling the state and processing in traditional network functions, stateless network functions, on the other hand, can overcome all of these challenges. With stateless network functions, if a process fails, we can spin up a new one and retrieve the state from data store. If we need to scale in and out, we can launch and terminate processes without having the need to manage state among them as it's centralized. This also gives us the unique feature that is not available in other solutions. By having a centralized state from all different network functions in the network, we have a system that is much simpler to manage and monitor. But if we already saw such approach in other systems, and it makes sense to decouple the state from processing, so why wouldn't see it in network? The why not is because of performance. By moving the state into a remote storage, an overhead is added. Since with network functions we need to handle millions of packets per second, it seems impossible to decouple the state without sacrificing performance. But we show in that work that is indeed possible. Here's some intuition as to why. First, there is not a lot of back and forth with a data store. It's simply a lookup stage in a processing pipeline. Second, requests to the data store are much smaller than the packet themselves. So we're not overwhelming the network or the data store. And third, there have been recent advances in low latency technologies, such as data stores and network as I/O. And we can really leverage these to create a high-performance system. Stepping back to elaborate, here we show an example of how state is accessed. This is a load balancer where there are two tables, a list of backend servers and a mapping of assignments. In the first packet of flow, there is a read to see what the packets are available, choose one, and then write the selection to the assigned table. All other following packets simply read from the assigned table. After examining different advances in recent technologies, we decided to build a complete system to show how stateless network functions can be deployed. We call our system StatelessNF. The StatelessNF architecture consists of three main components: the network functions themselves, which run on commodity servers; the data store, which maintains the network function state; and a controller, which orchestrates the entire system. Starting with the data store, in our current setup, we're using RAMCloud system. It's distributed, so it has built-in resilience, but at the same time, designed with focus on high throughput and very low latency with its read and write operations. Although the system can scale to thousands of nodes, extending functionality beyond a key value store can help improve the overall system, such as timers, atomic updates, and queues. Next, the network functions. This has a few aspects to highlight. First, we're capitalizing on advanced and high-performance I/O, such as DPDK and netmap, which bypass the kernel. Second, beyond the I/O, the internal of the processing is set up as pipeline, as is traditionally done in network processing. In our case, we package these up as containers. This allows to rapidly scale both within a single server to more cores and between servers. And finally, we optimize the data store client interface to capitalize on knowledge of the domain. Specifically, we have integrated a smart batching mechanism to reduce the request and capitalize on multi-read operation. We also utilize a buffer pool to eliminate overhead and enable a really high rate of sending requests. There are certainly more optimization we can make. Our controller handles the failure and scaling. It interfaces to an SDN controller to redirect the traffic to a network function instance. And that can be simple, as we don't need to worry about flow affinity. Interestingly, we have the benefit of being able to speculatively handle failure, as there's near zero overhead for failing over a like existing solution. So our detection time can be much lower. This is all implemented with the technology shown here. I'll note that while we did use InfiniBand, we're not reliant. RAMCloud now has DPDK support, and the latencies are higher. But we can largely mask the latency, since the total latency, as we will show in the evaluation part, is greater than the difference. And we can simply adjust the batching. Now, we designed and implemented our system. Let's see how it performs. Our goal in the evaluation was to see, in the extreme case architecture, where everything is physically separate, whether we could get similar throughput and latency to other solutions with better handling of resilience and failure. Our setup, as shown, we have a traffic generator and a sink, and a collection of servers in between, which host the network functions. We tested the throughput and latency and what the impact on the traffic when failure or scalability events occur. We performed the test on 3 deployed network functions: firewalls, load balancer, and NAT, where the state is decoupled into a remote data store, and compared them to a baseline network functions where state is coupled with processing within a single instance. First, we measured throughput. We evaluated our system under different traffic characteristics. On the left, we show the raw packet per second, which we measured by sending packets of the same size as fast as we could until loss occurred. We can see that with stateless, the throughput is lower for minimum size packets, but matched the rate at about 256 byte packets. This was due to hitting the limit of the data store, of how many requests the data store can handle. We will elaborate on this in the discussion part. But even with that, the rate match or exceed other systems which have added support for scaling and resiliency. On the right, we measured using an enterprise trace, which we replied by different speedups. The stateless version is within a few % of other baseline version. We expected that we will be able to overcome the challenge with the throughput, but latency is the biggest concern with decoupling. Shown here is our measured latency for NAT. The firewall and load balancer were similar, results are all on the paper. We will note that 15th percentile has 100 microsecond latency increase, and the 95th percentile has about 300 microseconds. Recent solution was designed to reduce latency, reported about 300 microseconds. So we align with that. In terms of scaling, we wanted to see the impact of the network traffic when we scale the network functions in and out. We ran our experiments on firewalls where we gradually increased the traffic rate, and about 4 gigabit per second, we arbitrarily said that that's the threshold to scale out. So we launch another network functions instance and split the traffic to it. Then at 8 gigabit per second, we gradually decreased the traffic rate and scaled in at 4 gigabit per second. Note that the stateless scaled perfectly with no loss, while the baseline version experienced significant disruption. And finally, failure. We submitted 500 HTTP requests to download through stateless and baseline firewall and induct failure. Once the controller detects the network function failure, it redirects the traffic to a backup instance. As we can see, a stateless had perfect time to complete, matching the case where there was no failure. And traditional baseline firewall has much longer time to complete. Details are all in the paper. We acknowledge that we will ultimately be limited by the scalability of the data store, but generally view data store as an active area of research. That said, other systems such as Farm and AlgoLogic report better throughput and latency, so we have the choice to use them. Another aspect, if we can further reduce the interaction with a remote data store. Each data store instance has limitation in terms of how many requests it can handle. So reducing the interaction with it increases the overall performance. We can do that by following techniques such as reducing the penalty of read misses by integrating a membership structure, for example, a Bloom filter. Or another approach is explore a placement of data store instance, perhaps even co-located with network function instance. In conclusion, we are motivated by the desire to make the network, specifically the network functions, more agile. In contrast to existing approaches, which built on top of the appliance architecture, we designed from the ground up and ended up with a design with zero loss scaling and zero loss failure handling. We showed that the main stated potential drawback, performance, is actually not a problem. There is certainly much work to do with further optimization and exploring point to scale out at the extreme case, as we will evolve in the data store to be more domain specific. Please come to see our poster at the poster session where we talk about the recent work on this. With all that, I'll be happy to take any questions. Thank you.
Hi, I'm Panda from UC Berkeley. So one thing about your evaluation is you focused entirely on workloads where there isn't where the shared state is easily partitionable. You talked about this thing of asymmetric paths. If you have asymmetric paths, how do you deal with things like contention? Similarly, in the suggestion you made that you could reduce interactions with data stores, how do you deal with data store consistency? The general problem is we know that share nothing scales great. You're saying that shared everything could also scale. So do you have results on where you actually have contention as opposed to this sort of...
So you asked me 4 questions.
No, it's one question. It's just one question. Where do you know what happens when there's contention? So suppose you have an asymmetric path. I'm updating, and you're also updating the same value. Have you seen what the performance comes down to? And do you know what happens as you scale up for the shared state?
Yeah, in the current work, we didn't measure that. So we keep it that for the future work.
But then couldn't any shared nothing architecture work for you?
Well, it depends on is it shared between flows or shared between instances. So for now, we are focusing on the share between flows, among flows, not among instances.
Okay, thanks.
Hi, this is Murad from University of Michigan. Nice work. I have a quick question. Were you aware of the OpenBox work that appeared last year in Sitcom? Because that work also proposed exactly the same thing, to decouple the processing and states of network function virtualization. I checked your paper. That paper was not cited. I just want to know whether you were aware of that work.
So we proposed this approach actually in Sitcom 2015. We had a workshop where we proposed this exact same architecture. With today's system, we built a complete system with the 3 different applications. The workshop was all.
So how is it different from OpenBox?
I didn't look at the OpenBox.
Okay.
So
yeah, you should check it out.
Take a question from here.
I'm off the ETH Zurich. So I just trying to understand what happens when a packet flows through a system. So you're doing a state lookup. In a typical sort of scenario, you're doing a state lookup to your data store for every packet, or are you doing this essentially a sort of caching some sort of results in your processing pipeline, to get some sort of locality?
Yeah, that's a very good question. So in the paper, we talked about different applications which has different patterns of read and write to the data store. So for example, for the firewall, we do a TCP handshaking. So like we do like read and write for the first 3 and the last 2, and the remaining of the packets are going to be read. The read, we can do it like per packet, like for every packet. For the write, it depends on the application. So for TCP handshaking, is different than, for example, a load balancer.
Right. Well, my concern is that by centralizing your data store, right, you are dramatically increasing the cost of a cache miss, effectively a cache miss on your processing pipeline. And as soon as you do that, you end up being vulnerable to adversarial traffic patterns, where somebody just sends a load of packets that don't interact well with your caching strategy, and suddenly your throughput dies because you actually can't access the data store fast enough at that point.
Yes, so we actually experienced the read misses, like especially with the new flows. And as I mentioned in the conclusion, that now we are actually implementing a Bloom filter, and that's we're going to reduce the amount of missed reads, if I understood your question correctly.
It's really more about people crafting traffic patterns that will deny service.
Mm-hmm.
I don't know if you looked at that kind of, what's the worst traffic you could, can you deal with the worst case traffic pattern?
So we like for the throughput and latency, we experiment like with the 3 traffic patterns. One is like large number of flows with a small packet size, and the other one is the reverse, and the third one is like an enterprise trace. So we try to cover different aspects of that.
Right, with that, let's thank the speaker.